Take it away, Ofri.
All right. Well, it's a pleasure to be here, and thank you so much for the invitation. And I would like to tell you a little bit about things that I've been thinking about for the past maybe 2 years or so, and has led to some developments that have been quite exciting for me. Essentially, the idea was to tackle a problem which is inherently hard from an action formalism and QFT formalism, and to try to tackle it using on-shell methods, kind of showing this or demonstrating the promise of on-shell methods is an alternative way to attack quantum field theory problems that could succeed where traditional methods fail. And I think this is, in essence, a very interesting problem because it's an inherently non-perturbative problem. Because if you talk about the scattering of monopoles and charges, E times G, the magnetic charge, is quantized, so everything is non-perturbative. So you think that I have nothing meaningful to say about the system. But the flip side of it is that there are long-range electromagnetic interactions which deform what we mean by angular momentum in the presence of charges and monopoles. So that gives us modified selection rules that are very powerful from an onshore perspective. So powerful that using these tools and developing the right technology to talk about them and present them in a quantitative way, we were able to derive monopole catalysis, which is this very kind of counterintuitive notion that if a proton falls into the dot monopole, somehow it'll catalyze proton decay. And that process is non-decoupling. So it doesn't decouple even if the monopole is very massive. So from the fact that this process is non-decoupling, you can already think that there's some sort of angular momentum selection rules that underlie the process. And maybe this process could be understood without opening the box and doing the hard quantum field theory, but just looking at the asymptotics of the scattering process, which is what we did. So let's get going. So just kind of setting the theme for this talk, I was walking around here, or maybe it isn't actually.
Pointer work?
Pointer work? Let's see about the pointer. Pointer works.
Just do the regular clicks.
All right, so I think there's just a response time between my computer and everything else.
Yeah. It's fine on Zoom.
Okay,
Someone on
sure.
the chat is saying something. Maybe they
No,
know how to fix it.
that was me.
Oh,
Not saying
okay.
it.
Okay, so I was walking around here and I already saw something that triggered me a little bit.
Yeah, no magnetic monopoles is our policy.
Yeah, this is like literally written on your wall.
That's
And it seems quite asymmetric and unkind to the monopoles. So I just decided to fix it this morning. And put, well, the joke is lost, but in a few moments.
comic delay.
Yeah, I mean, is there a way to?
I'm not really sure what's
Reconnected to the Zoom.
Yeah, I am.
It's a computer here that's slow. I'm not really sure why it's doing that.
That's still, even for it.
Yeah. Maybe it's doing an update in the background. I'm sorry, I don't really know. I don't know why. Hopefully.
Is there a way to put like a hard copy of the presentation on this computer and then?
If you have HDMI.
I do
Yeah,
have
that works.
HDMI actually.
Okay.
Yeah.
Let's see if that works. Anyone ever use this? I don't know how your click thing works.
Yeah, and then you do the presentation. Yeah. Okay, and let me see. What's now?
Yep.
Yeah, okay.
Still works for everyone on Zoom?
Okay, and the clicker works too. Good.
Very nice.
All right. So once we fix this, let me kind of set the stage and tell you what I mean when I say monopole. So for me, a monopole is just a source of a radial magnetic field under U1, which might as well be U1 electromagnetism, but it could also be a different U1. In the case of gut monopoles, it's a U1 which is a linear combination of electric charge and a new one which hides inside SU3 color. At radii larger than their core, they're effectively abelian. They're like point sources of this B field. Of course, when you approach their core, there's some UV physics here, which might be just non-abelian gauge theory in the case of topological of monopoles, or it might be string theory or something else. For the purpose of this talk, we won't really look near the core, because that won't be necessary for our instruction. And they also lead to charge quantization, famously by Dirac, and also formulated in a more topological language by Wu and Yang, that talked about a two-hemisphere definition of the gauge field around the monopole, which is sewed on the equator. And then for consistency on the equator, you need Dirac quantization. And we will see, by the way, as a side comment, that charge quantization, which here comes from topology, in our construction will come from group theory. So there's going to be this non-trivial marriage between topology and group theory, just representations of the Poincare group. And in future work, which I hope to publish in the next few months, we'll show how it also connects to field theory and analytics, and to basically the dressing factor for electromagnetic scattering. So it's like a three-way connection between topology, group theory, and analytics. Now, you could ask, why focus on magnetic monopoles? Well, I like this statement by Kulczynski. The existence of magnetic monopoles seems like one of the safest bets that one can make about physics not yet seen. And indeed, in string theory and basically every theory of quantum gravity that I know, the completeness conjecture, first stated by Banks and Seiberg, I guess, first stated by Kulczynski, but expanded by Banks and Seiberg, claims that there should be a manifestation, a particle that carries every allowed electric charge and every allowed magnetic charge under every symmetry in the problem, every gauge symmetry in your theory. And the reason is that if I'm missing one of my monopoles or one of my charges, my theory is going to have a global symmetry. That's a global one-form symmetry, which is unbroken, and I don't have charged matter. And because we believe that there are no global symmetries in gravity, we think that all global symmetries have to be broken. So there has to be some particle carrying this given electric and magnetic charge for every charge that's allowed by Dirac quantization. So this is what makes it a safe bet in theories of quantum gravity. Of course, that doesn't mean that it's going to be detectable in low energy, but it still means that we're studying something that might as well exist in nature.
By particle, you mean stable particle?
Yeah.
So for instance, there should be stable particles like charged 10 times the electron charge, or?
Yeah, I mean, there should be, a state in theory. I don't know what mass it has. Okay, it could be close to the Planck scale. But if that particle doesn't exist, there's going to be a one-form symmetry that's unbroken.
I think you just need a unit charge guy to be
Yeah,
stable, and that's
that's-
sufficient.
yeah.
Being sure there's no one form
that-
symmetry.
You can form bound
Yeah.
states.
Yeah.
You can
Right.
Just for
right,
the
right, right.
ignoramuses, what's a one-form symmetry?
I agree. I don't really want to get into that in this talk because it's really far removed from the topic of the talk, but I'll be happy to discuss
But the
this.
example of that is center symmetry in QCD. That's probably what I'm that's a classic example.
Okay, good. So once we set the stage and we state that there might be monopoles in nature, though we can't pinpoint what mass they are and whether they'll be phenomenologically available, we can talk about all kinds of QFT processes that are very counterintuitive that happen when fermions interact with monopoles. And these things happen in the lower energy EFT around the monopole. So for example, Kazama, Young, and Goldhaber did a very interesting exercise. They solved the Dirac equation in the presence of a monopole. And what they found is that when a wild fermion of the given helicity scatters into the core of a monopole, and you don't need to know anything about the core itself, just the EFT around the monopole core, it has to flip its helicity, and that comes about just from a solution of the Dirac equation. Later in this talk, we'll show that there's actually a selection rule that you can formulate in the language of the S matrix that forces this to happen. This is part of the theme of the talk. And a slightly different variant of this is the famous monopole catalysis by Rubakov and Callan that shows that gut monopoles catalyze proton decay. So specifically, if I throw a proton at very low energy into a monopole, the proton has a U when these labels are labels of color. And the reason that we differentiate the color labels is because the long-range charge of the monopole is a linear combination of the U1 that sits inside color and electromagnetism. So this is why you can tell the difference between different colors. A U1 and a U2 falling into a monopole have to emerge as a positron and a D3 dagger and a monopole. So this was analyzed by just solving the field theory, the effective field theory around the core of the monopole. But it's still, there are still non-intuitive questions about this process and other processes which are called the monopole catalysis paradox, which I'll explain below. And we managed to prove that this has to happen at the lowest partial wave for fermion monopole scattering just by virtue of angular momentum selection rules. As a phenomenologist, I would also ask why should I care about these processes? Well, these processes are big, are huge. They're non-decoupling, even though the monopole could be very heavy. So they're essentially the cross-section for this saturates the S-wave unitarity bound. When we talk about these quarks being dressed inside a proton, we're talking about cross-sections are QCD scale. So if you run the math and you just open Cobb and Turner, you see that if there are only 10 to the 28 monopoles in the sun, they could generate through proton decay the entire luminosity of the sun. This is a demonstration of the magnitude of the effect that we're talking about because it's non-decoupling. And also the leading bound on the existence of gut monopoles, it's counter to what most people think. It's not because of overclosure. It's much more stringent because of the possibility of monopole capture in neutron stars followed by catalysis in the core of the neutron star, and that gives a dominant bound by 10 orders of magnitude. So we're talking about a counterintuitive non-decoupling effect that is understood from a field theory perspective, but seems like there should be a complementary understanding of it, which I'm going to present in this talk. But like I said, you could just run the microphysics of this effect. And the microphysics is that there's some non-perturbative interactions of the fermions with the monopole collective coordinate, and that interaction is non-decoupling. And that's a traditional QFT approach, which we're not going to take in this talk. However, we will show that you can also explain by macrophysics. Essentially, the angular momentum operator J is modified in a monopole background. And the reason for it is the long-range electromagnetic interaction between a charge and a monopole, and I'll explain more. Once you take into account the modification of J, the modified selection rules plus charge conservation could pinpoint exactly monopole catalysis and the fact that it saturates the S-wave unitarity bound. So let me tell you about the content of this talk. First, I'll present our construction of the S matrix for charge and monopole scattering. Then I'll use our construction, basically generalized little group arguments for the modified S matrix to nail down all 3-point amplitudes for different dyons, charges, and monopoles. This is kind of similar, if anybody knows here, the paper that Nima wrote in 2017 about scattering amplitudes for all masses and spins. So using little group, he was able to nail down all 3-point amplitudes. This is the version of this paper in the presence of electric and magnetic charge. Then we write down the most general partial wave decomposition for charge monopole scattering and derive the helicity flip effect. And finally, using our technology plus charge conservation, we'll be able to derive the Callan-Rubakov effect of monopole catalysis. And we probably won't have time, but you can ask me about the monopole catalysis paradox. So let's start. We're talking about Dirac monopoles here. These are just point particles as far as we're concerned. Since the days of Dirac, there's no clear way to write a local Lorentz invariant Lagrangian for Dirac's monopoles and electric charges. Our Schwenker tried it, and what he wrote down is a manifestly non-local Lagrangian, though it was still Lorentz invariant. The other approach was developed here at NYU by Daniel Twensiger, who, on his work, a lot of our intuition is based. And a lot of what we did is we took an idea that was in the gem of a paper that he had from 1972, I think, and made it into an industry. So a lot of this started actually here. And the first thing they did is he wrote down a local Lagrangian, but the cost of loss of manifest Lorentz invariance, because they introduced a definite direction, which was the Dirac string that existed in the Lagrangian. Now Weinberg did the same thing. He had Lorentz breaking Lagrangian, and he wanted to calculate the scattering amplitude, just a one photon exchange between the charge and the monopole. And he calculated it, and he said, okay, if the amplitude is string dependence, but when I square it, I get a cross section which is manifestly Lorentz invariant, that would be fine. But then he squared the amplitude, and he saw that even the cross section was Dirac string dependent. So his conclusion was, this is nonsense. There's no quantum field theory of a billion monopoles interacting with charges. But it seems like Weinberg was wrong, and the reason he's wrong is Weinberg himself. Because what he should have really done is he should have summed the entire ladder of photon exchanges between the monopole and the charge. Because as we said, this problem is inherently non-perturbative. If a photon couples to the charge with an E, it couples to the monopole with a G. E times G is an integer. There's no meaning for just one photon exchange. And indeed, once you sum up the entire ladder of exchanged photons, you find that the string dependence, the Lorentz breaking, exponentiates the phase, which vanishes when you take the absolute value squared. So that is to say that.
But sorry, but it's not true that one cares only about cross-section, right? Because there are like interference effects which are encoded in the phase.
Exactly. So there's a beautiful paper by my collaborator John Turning and company, in which they show that the phase that you incur if the charge goes in a circle exponentiates to e to 2 pi times the linking number, the string in the path, the trajectory of the charge. So interference is okay. It's okay. Good. So Zwanziger had a local Lagrangian, but there was a manifest loss of Lorentz invariance. But the S matrix, if you calculate it right, is completely kosher. It's a local, it's Lorentz invariant, and up to a phase because the Dirac string exponentiates to phase. But somehow there's an impediment to describing it in a Lagrangian language. So what we thought is, can we just construct the S matrix without ever thinking of a Lagrangian? And that's indeed what we did following Zwanziger's lead. So the first thought is that Dirac quantization should play a leading role here, because Q, which is E times G, is half integer. And can we think about other half integers in the construction of the S matrix? Well, these are helicities and spins. So there should be some meaning of the Dirac quantized quantity as an effective helicity. However, the second thought that you have here is, wait, helicities that are associated with single particles, but E times G is associated with pairs of two mutually non-local particles. And this leads us to this concept of pairwise helicity. This is effectively a quantum number in the S matrix, quantum number in the sense that it's just like a helicity, but it's defined for pairs of mutually non-local particles. Any questions so far? Good. So let me tell you why, already at the classical level, there's something funny about the scattering of charges and monopoles, and there's a modification of the angular momentum problem. Let's say I take just a static charge here and a static monopole here, and I do the exercise of calculating the angular momentum that's locked inside the electromagnetic field. So what do? I take the pointing vector, I cross it with r, the position vector, I integrate over all of space, and using identities on the cover of Jackson, I find that the result is minus E times G times r hat, which is the direction from the monopole to the charge. This is distance independent. That's crazy. I take now the monopole to another galaxy. Because I integrated over all of space, I still have this irreducible angular momentum, even though the energy of the interaction between the charge of the monopole goes to 0 when I separate them infinitely. So it's still a local theory. However, it's a mutually non-local theory in the sense that there's this irreducible angular momentum problem. And note that this is a calculation that J.J. Thomson already did in 1904. So already then people knew there was something fun. And this is also the quickest way to derive direct quantization, because we say in quantum theory, this extra angular momentum has to be quantized, which means that this has to be half integer. So this was a one paragraph proof of direct quantization written by Saha in 1936.
In
Yes.
both cases, those were for magnetic monopoles.
Sorry?
So the example of Saha and Thomson really were doing magnetic.
Yeah. Yeah, even Poincaré tried to do it at first, but it was a little wrong in his derivation. Good. So there's extra angular momentum in the problem. Let's think purely classically before jumping into the S matrix, how this would modify the classical scattering of a charge on a very heavy monopole at the center. Well, the angular momentum now is the orbital one plus this extra electromagnetic piece. If you dot it with r hat, you get something conserved. That tells us that the motion is on a cone. So if this is a charge and this is a monopole right here, and you give it an initial velocity, that velocity defines a cone around the angular momentum, the total angular momentum. And from now on, the charge is constrained to move on the surface of the cone. It can wind around it, it can get close, but eventually it has to escape exactly on the cone. And if you solve the classical mechanics problem, you see there's a pattern of rainbow and glory angles here, where the scattering angle essentially depends on the opening angle of the cone, which in turn is dictated by E times G. And this is this pattern of rainbow and glory angles. And an interesting pattern here is that there's also winding of the trajectory around the cone. So this is not a talk about classical physics, though I think this is pretty cool. The lesson that I want you to take from here is that the constants of motion are actually deformed by the presence of the long-range electromagnetic interaction between the charge and the monopole, and the angle of the hard scattering is constrained to be on the soft cone.
But in the axis of this cone, so it points towards this charge which is infinitely far away, right? That's kind of
No. This is the charge,
right.
this is the monopole, and this is J total.
But so this R hat in the previous slide, right? So that's
Right. So here I use L not J, so L dot R hat is EG.
okay.
So that fixes you to be on the cone. Good. So this is already in classical physics an example of a non-decoupling effect, because if my winding trajectory moves close enough to the monopole, it's essentially probing the core of the monopole. Now in the core of the monopole, it's hard physics, is completely decoupled from the electromagnetic effect, and yet it can't just like escape in this direction. It's not allowed to by the selection rule that's derived from the higher physics, the soft physics, right? So this is kind of a classical example of essentially UVI or non-decoupling. And we'll see a similar thing in the quantum picture of the S matrix that will lead to things like the helicity flip and the Callan-Rubakov effect. So here's our mission. We want to scatter now quantum charges in direct monopoles. The quantum charges in monopoles source a classical electromagnetic field, which in turn deforms our definition of the angular momentum and feedbacks on the S matrix itself. How can we write a consistent S matrix this way? And just so we think a little bit in a QFT language, you can think of this extra deformation of the angular momentum as the dressing effect from soft photons exchanged to infinity between the charge and the monopole, before and after the scatter. And indeed, I was pretty happy to find out that something like half a year into this work, I was randomly reading Weinberg's book. I was reading chapter 2, and in his construction of the S matrix, he has this comment here that the J of the angular momentum of the interacting S matrix equals the J of the non-interacting S matrix, and the only known exceptions are theories with topologically twisted fields, such as those with magnetic monopoles. So at this point, you have to close Weinberg, and everything that is from now on doesn't really apply, and you have to kind of change the fundamentals of the S matrix to accommodate the deformation of the angular momentum, which is what we did. a lot of our intuition is based, as I said, on this work by Daniel Zwanziger, in which he showed how to derive an extra little group phase associated with the presence of charges in monopole. And we've made this into an industry and systematized the process of constructing electric and magnetic
Can I ask you about that diagram which you drew there? Because very naively, there is even then more dangerous corrections which can connect two monopole lines, right? Because that would be proportional to g squared, which is g times e is 1, but g squared is much bigger than 1.
Right.
So what happens to those?
Right. So in my mind, everything that's g squared and e squared is remedied by the regular Faddeev-Bullish dressing, and you just dualize the Faddeev-Bullish dressing factor. So instead of doing a Wilson line dressing, you do a Tufts line dressing, and that should cure the iron divergence.
But that would take that would be for like g squared factors where a photon connects the same line, right? And if the photon connects incoming and outgoing.
Oh, like this.
Right.
I think these should be also cured by Faddeev-Bullish dressing. So what we're talking about here is an effect that does not have an iron divergence. And the way that you can see this is in quantum mechanics. If you just do what the Zama and company did, they solved the Dirac equation in the presence of the monopole, you find that towards infinity, there's no Coulomb log in the wave function. So this is a finite effect. And indeed, in current work, we're literally calculating this dressing factor and finding that it's finite and doesn't have Norm divergences. So what we do is we're going to redefine the asymptotic multiparticle states of the S matrix to include this deformation of the electromagnetic J, such that when you act on the quantum state with the J operator, you're going to get a result which includes this electromagnetic contribution. These new multiparticle states are by definition not tensor products of single particle states, because now there's like a pairwise connection between mutually non-local particles. Now we derive the modified transformation rule for electromagnetic scattering, and we use it to construct amplitudes for monopoles. Okay, so this is the map. We start with electric magnetic multiparticle states, get to the low-level transformation of the S matrix. That gives a requirement, something that we need to saturate. So let me kind of explain the logic here. In usual scattering, you can say I'm scattering a fermion and a scalar, 2 to 2 scatter. Just by the fact that I said that it's a fermion scattering with a scalar, I know what the phase of the S matrix will be when I do a Lorentz transformation. The S matrix is not Lorentz invariant, it's only Lorentz invariant up to a phase or an extra little group factor. And I know what this factor is just by the fact that I said that I'm scattering a fermion and a scalar. Now I can go about and ask, how can I write down some formula for what the S matrix could be, such that when I transform that formula, its functional form will give me exactly the phase factor that I postulated that I need by saying that it's a fermion and a scalar. So that's how you do little group arguments to fix some of the angular dependence of the S matrix, just from the fact that you know what particles you're scattering. It's going to be the same thing here, only instead of putting the information that I'm scattering the fermion and the scalar, I would also have to say what their E times G is, which we call the Q, the pairwise helicity. So the pairwise helicity now comes into an input from which you can derive the required transformation rule of the S matrix. And now you can do the same exercise. You can ask, how the hell do I write down something that has the right functional form to transform the way I postulated it to be? Now you can construct it together by putting together spinor helicity variables. And we also define a new kind of spinor helicity variables which transform manifestly with the right phase associated with the extra phase that we have in the S matrix. So we have a rule of how the S matrix has to transform. We define Lego blocks that we can assemble together to construct an S matrix that has the right transformation, and that will enable us to fix a lot of the S matrix.
Sorry, I'm curious because I'm a little bit confused even of how to define this matrix in this situation, because where kind of it's about like it's like product in-out states, but in the definition of in-out states we use usual tensor products. Right. So what are you doing here?
Right. So we have a PRL in which we completely The PRL is called New Multiparticle Representations of the Poincare group. Now, the word new is a little loaded here because you can say, okay, Wigner categorized all the possible representations of the Poincare group. So these representations are not new in the sense that you can translate them into some known representation, but that's not useful. This new representation is a multiparticle representation, which is not a tensor product of single particles, because there are these pairwise connections and phases associated with charges and monopoles. So the whole PRL was to formally define this by essentially, well, I won't get into details, but I'll be happy to tell you about it.
But once you just to get an idea, at the very intuitive level, very roughly when we say, okay, in-out states, they correspond to turning off interaction. But when you have both electric and magnetic, as you say, you cannot turn off simultaneously E and G, right? So how to even...
That's right. So the point is, there's no meaning for the undressed S matrix for charges and monopoles. Whenever I have to talk about the S matrix, it has to be Fedorov-Coolidge dressed, and this dressing comes with its own little group phase, and that is what we're constructing here using algebra alone. So we're not going to say the word dressing, but now we're writing the paper that connects these two things. So here we're just postulating a group theory transformation rule, which we did the consistency checks to see that it has the right classical limit. In the next paper, we're actually proving this from Fedorov-Coolidge. Good. So again, just to recap, we're gonna show how to, given the identity of the scattering particles, to know what their little group transformation is. Then we'll define the Lego blocks that we can connect together to construct an S matrix that has the right transformation rule, and that will enable us to just fix amplitudes up to low group invariance. And in this way, we'll be able to fix all 3-point amplitudes, write down the partial wave decomposition from 2 to 2 scattering, and also address the Rubakov-Callan effect, and perhaps the monopole unitarity puzzle if we have time. So let me see how the time was.
There's a clock there, you have 25 minutes.
Oh. Good. All right. So, like we said, the usual multiparticle states that we know are characterized by momenta and single particle spins and helicities. So these are just complete tensor products of single particle states. I can ask, how is the Lorentz transformation represented with a unitary representation on these quantum states? Well, you got the Lorentz transformation acting on the momenta, and you have an extra factors which might be SU2 matrices or phases, depending if it's a massive or a massless particle. And this is a product over just the individual particles. So there's no pairwise connection between different particles in the multiparticle state. Our modification is that multiparticle states that have to do with mutually non-local particles, in addition to the momenta and the single particle spins and helicities, they have new quantum numbers that are associated with every pairing that I could have. Some of these will be 0. For example, if I have 2 charges, not a charge and a monopole, the associated Q here will be 0, and they will just behave as a tensor product. But if I have 2 mutually non-local particles, then I'll have a half integer here, which is non-zero, which will give me a different transformation group. So these Qs are the EIGJ minus EJGI, and they're quantized by Dirac, the Swanziger-Schwinger quantization. This is the quantum manifestation of this X-Rangel momentum that we saw in the classical example. And we can show it formally by taking the classical limit of the quantum scattering amplitude. So how do these things transform? So I told you that they have extra labels. These extra labels have an effect when you act on it with the unitary representation of the Lorentz transformation. In addition to the single particle matrices and phases, I have a sum here over the pairwise helicities times the little group phases, which we have a formal definition of. Basically, to define these, we formally define them in our PRL. This is repeating the process of the usual definition of the S matrix through Wigner's method of induced representation, only working in pairs. Now I have a reference state, which is the center of mass of the charge of the monopole, and there I define the unitary representation of the little group, and now I boost it to any other frame, and I get a phase here. So I'm being intentionally vague here. There's like, behind what I just said, there's a lot of math that I'll be happy to get into, but if I got into now, you won't see the results till the end of the talk. So I made the executive choice of not getting into definitions.
These are sums of products, can be written as sums of products of one particle states. So take these two particle states, can you write it as entangled sum?
Yeah, I can. So tensor products of single particle states are a basis for that space, but I'm probably to represent this on the basis of just direct tensor products, I would have to have an infinite amount of terms, probably, to do this transformation. Yeah. Good. So electromagnetic multiparticle states are not, should be tensor products here. The pairwise little group phase is similar to how you do the Wigner method of induced representations, and this is just for, we won't get into the details, but please ask me if you're interested.
So your S matrix will not be defined on the tensor product of one particle space, only on a subspace.
It will be defined on these. So take this within, dotted with this without, that's the S matrix, and that's probably the next slide.
Yes, but again,
So it's not a conventional Fock space, that's essentially what I was asking, right?
Right.
It's on this.
Right, I take the mathematical definition and
so but that, okay, but I'm trying to understand the physics here.
Mhm.
I know enough of math for that. So your S matrix is defined on a subspace of the tensor product, right? Where you only say, yeah, 1, 2 plus, I don't know, 3, 4, just to make an example, but not on the factors.
I'm not sure I understand.
Well, take a product of the Hilbert space of single particles, right? Just the product, the three tensor, the tensor
Yeah.
product.
So
That's
it's not
the-
going to span this.
So not even as a linear combination.
No, because I need the single particle states for all of them, and it's a von Neumann space of an indefinite number of photons. I need the soft photons here.
I see, okay, so that's
Just photons. This phase essentially comes from the soft photon.
And so this your S matrix will not obey any cluster property.
There's no crossing symmetry.
In cluster also.
Oh, cluster. That's a good question. People ask me that, and I need to think about it, but I'll be happy to talk about it. Crossing symmetry is something that you don't have. Because, I mean, this extra angular momentum is associated with in particles that out, but not in out. We have to live in the same time.
That's basically because scattering of electron monopole is kind of strong, but monopole pair production is always non-perturbative effect, right? So that's
Good. So now the S matrix is taking these multiparticle states that we define and just labeling one in and one out, and we can work with the usual Weinberg definition of wave packets that go to free states in the infinite passive future, free up to the dressing factor. And then we can ask, how does the S matrix transform? So the S matrix, as you remember, is not Lorentz invariant, it's Lorentz invariant up to a little group phase. And that's what we're after. From the transformation rule of these states, we know that the S matrix incurs these single particle low group factors associated with the individual particles here. And there's also a sum, which is separately over all in states and out states, which is the sum over the pairwise helicities and the low group phases associated with it. So this is, once you specify what you're scattering, fermions with charges E is this, G is this. This is postulated. This is what whatever S matrix you write down, you have to saturate this transformation rule. Now I'll give you the Lego blocks to put together to construct S matrices whose functional form reproduces this extra factor.
sorry, that's related to my previous question. So then that extra phase, in some sense, is unobservable in any interference, right? So because from here it sounds like S matrix really defined only up to as an additional phase because it's not invariant on the Lorentz transformation.
Right.
But the phase in principle is observable in the S matrix. And so in this phase somehow is not.
Sorry. The string dependence drops out.
Right.
But this phase is not just the string dependence.
This E2, like,
Yeah, this is more than just the string dependence. This is a group theory.
but does it mean then the S matrix is not Lorentz invariant? And like
No, this is not. And this is on the same footing as single particle rule. Whatever is true for single particle is true. So just like you have these D.
So that function phi, you know it now, or
Yeah.
it's a known function now?
It's a little group phase. So let me tell you what it is. What I do is for each pair of charge and monopole, I go to the center of mass where their momenta is back to back along the z-axis. Now I ask what subgroup of Lorentz transformations keeps them fixed. These are just U1 rotations, and this is why it's a helicity. So a helicity is just labeling the representations under this U1 rotation, which keeps these reference momenta back. And now I have a canonical Lorentz transformation that takes these back to back to any other direction. And what I'll have is now an associated phase, which is, it has to be a rotation around the z-axis because that's what my little group is. And just like in the Wigner construction, it's the canonical Lorentz transformation taking you from K1, K2, the reference momenta, to the finite momenta, followed by whatever Lorentz transformation you're doing, followed by the inverse, L-1 of lambda b. And this is how you can literally calculate what this phase is.
That's a cocycle, right? This phi. I mean, it cannot be eliminated by redefining the phases of the initial states.
Yeah.
You could choose a preferred frame, say rest frame for massive particles, and then boost to another frame and get factor 5, but then
Right.
you may not, when you do two boosts, you may still get.
So it's the same thing as the single particle little group for massless particle, right? You can't get rid of this extra phase. Good. All right, let me jump ahead a little bit. So now we have a postulated transformation rule, and we need the Lego blocks to construct the S matrix. So we have the usual Lego blocks that have nothing to do with monopoles. These are spinor helicity variables. There are massless ones associated with massless particles, and there are massive ones associated with massive particles. And the important thing to know about these things is when you act on them with a Lorentz transformation represented in spinor space, what you get is just like in the quantum state, you get a lambda acting inside the ket on the momentum itself, but you get an extra factor. Now, if you use these with the spinor indices contracted to construct the functional form of the S matrix, it'll transform with this extra phase, saturating the required phase that we know from the quantum states. So here, this is essentially transforming like a helicity plus half, and this is transforming like a helicity minus half. And these have the same massive little group factors as the quantum states. So this is why these are good Lego blocks, because they have manifestly the transformation matrices that we require from the quantum states. But if we want to talk about monopoles, we don't have enough Lego blocks now. Because what if I have a massive vector dyon decaying to a massive scalar in a massless vector monopole? So this amplitude right here. And by the fact that I said when I'm scattering, I already know what the required little group transformation is. I know that there are two single particle phases here, but there's this extra annoying phase here. And no matter how many regular spinor helicity variables I'm going to put together, they're never going to transform with this extra phase for any Lorentz transformation. So I'm missing a building block here, and this is what I'm going to define. I'm not going to get into exactly how I define these, but I can define new spinor helicity variables, which are essentially the cousins of massless spinor helicity variables because they have an extra U1 phase. But this time, these are associated with pairs of particles in the amplitude. That's why they have IJ labels. And they also have plus minus labels that come with plus minus in the phase transformation. So I can manifestly construct these spinor helicity variables that are just functions of the angles and the magnitudes of the momenta in the problem, such that they have exactly the right transformation rule to saturate the quantum transformation rule of the quantum states. So now these are completely good building blocks. And now I just run with it. I can say what I'm scattering. I can put together the old spinor helicity variables and the new ones such that they saturate the right transformation rule. And voila, I fix the form of the S matrix up to a little group invariant. Questions about this? Good. Now, an important thing, which is crucial to the fact that we have the helicity flip and Callan-Rubakov and all this, is that the definition of the pairwise spinors comes with a selection rule, which will tell you that some combinations vanish. And this was what will tell us that, for example, if I throw a proton on a gut monopole, it can't just leave as a proton. That the amplitude for that forward scattering will be forbidden by the fact that if I dot the usual spinor helicity variable for a massless particle with the pairwise spinor that I just defined, the answer is 0. So there will be many, many amplitudes I would like to write down at the lowest partial wave of the scattering, which will be true by any measure possible, besides the fact that these things are 0. This will be the angular momentum selection rule that leads to these very counterintuitive effects. Good. So now we can get to results, because what we did is we defined the quantum states, we defined the S matrix and its required transformation rule, and we provided ourselves with the tools to construct analytically the required S matrix up to a little group invariant. And now we can just use it to fix amplitudes. And by the way, our results are fully non-perturbative, because we never expanded anything. Great. So there is a one slider, the fact that we just wrote down all 3-point amplitudes. So 3-point amplitudes, the little group, and there are no manual stamps that I can write. So if I nail it up to a little group transformation, the prefactor could just be a number, 2.5. So up to that number, we just nailed down the functional form of all scattering amplitudes for dyons, monopoles, and charges. So one result, for example, is that, let's say, so S hat is the sum of the of the spins of the 3 particles. Let's say I have 3 scalars scattering. If there are 3 scalars, then S1 plus S2 plus S3 is 0. So that means that the relevant Q, E times G, minus EI minus EI times GJ minus the opposite combination has to be 0. If you put that selection rule plus charge conservation, you find that a scalar dion can't just decay as 2 scalar dions unless there's a duality transformation that takes all these dions at the same time to charges. So this is just, these are not really dions, these are just charges in disguise. We learned that without ever studying the microphysics of dions. We learned that just from charge conservation plus the selection rule, which comes from our construction of the S matrix. And similarly, all these 3 other selection rules are modifications of of the selection rules that Nima writes for all masses and spins that have to do with the Q, the relative E times G minus G times E of the scattering particles. Okay, so we wrote down all 3-point amplitudes. Let's see what we can do for 2-to-2 scattering, and specifically if we can understand the helicity flip. So going back to Kazama, Yang, and Goldhaber, who solved the Dirac equation in the presence of a monopole, they found several counterintuitive results, which we now explain. One, they found the main thing that you do in quantum mechanics is you scatter a plane wave on some potential, and you expand in spherical harmonics, and the partial wave decomposition starts usually at 0. You have an S wave. Here, the partial wave expansion doesn't start at J equals 0. It actually starts at the magnitude of Q, which is E times G, minus a half. Why? Because of this extra angular momentum associated with the charge in the monopole. The other counterintuitive result is that spherical harmonics are no longer spherical harmonics. They're actually deformed by the presence of this extra angular momentum. They become monopole spherical harmonics. This is similar to, if you're familiar with solutions of the Minkowski equation for Kerr black holes, these are the angular functions.
So how are they defined? I mean, usual way.
They're related to Wigner D matrices. Yeah. And I'll show how to get them in a few slides. And the most counterintuitive thing, if I just have a massless left-handed fermion, scatters on the monopole, it emerges as a right-handed fermion. And the cross-section for that saturates the unitarity bound for the lowest partial wave. So it's a non-decoupling process. Let's see how we can just derive this in almost one line using our formula. So I'm scattering a fermion on a monopole. I have to saturate on a scalar monopole. I have to saturate the single particle little group of the fermion, incoming and outgoing. This is why I have this massive spinor helicity variable for the fermion. And I have to saturate the pairwise helicity. So I have to have this entire construction transformed correctly under the pairwise little group. But I know that this is like a pairwise helicity half. This is another one, another half, another half, another half. I can put them together, exactly the right number of them. I know how many free spinor indices are contracted between the in state and out state, because this is just 2J, when J is the partial wave done in. So essentially, little group enabled me to fix everything here up to a factor which is little group invariant. Now here's a surprising fact. If you take this symmetric contraction of in state and out state, the result is a Wigner D matrix. It's exactly this monopole spherical harmonics. So instead of solving the whole Dirac equation, I took the spinor helicity variables with the right transformation rule, symmetrized and contracted them, and got exactly the result that I could get from solving the wave equation. So this is essentially the Jacob-Wick formula for 2-to-2 scattering, partial wave expanded, and it's this single particle factor times the D matrix, which has an indices here, the Q's. So the D matrix has an angular dependence that depends on the E times G of the charge in the monopole. So let's see how all the things that Kazama found are just derived from here. They're just derived from the fact that if these labels are more than the J here, the D matrix vanishes. So the D matrix vanishes unless the J is larger than Q. So that gives me exactly this fact that the partial wave decomposition doesn't start at 0, it starts at Q minus a half. The Wigner D matrices are equivalent to the monopole harmonics, which we now define from the bottom up. And last but not least, at the lowest partial wave, when J equals exactly Q minus half absolute value, if Q is negative, I can only choose these signal labels such that it's a right-handed fermion going to a left-handed fermion. And if Q is positive, I can only choose them both to be minus. In that case, it's left-handed going to a right-handed. So we're proving by our selection rule that the amplitude has to be 0 unless there's the helicity flip process. What's the flip side of this? If an in state could only have one single out state in this partial wave, then the cross section for that has to saturate the S wave unitarity bound. The unitarity bound for the J equals Q minus a half, right? So this is a non-decoupling effect. It has nowhere to go. A right-handed fermion can't stay right-handed. It has to go left-handed and the other way around. And we'll use a very similar technology to prove the Callan-Rubakov effect. So, questions?
But
Yeah.
you have
No, yeah, I understand. Okay. Good. So let me just tell you a very short version of how you do Callan-Rubakov with it. So I already showed you how selection rules lead to the helicity field. In Callan-Rubakov, the only extra ingredient that you have to put in is standard model charge conservation. Nothing else. So these selection rules, together with standard model charge conservation, will lead to only one allowed process at the lowest partial wave, which is that these U's are converted to an E and a D. So this is just an intro to SU5 GOT, which you don't need at this stage of the talk. All we require is standard model of charge conservation and the fact that the monopole is blind to an SU4 global symmetry, linking different multiplets that the multiple just doesn't know the difference between them theory-wise. So putting the data of standard model charge conservation, this horizontal symmetry, which is not an extra postulated, it's not something extra that we put into the problem. We get monopole catalysis. So in the same way that we wrote the amplitude for the helicity flip, we can write the instate, which conforms with the transformation rule that we need for the S matrix. So we need the single particle transformation for the U1 and the single particle transformation for the U2, saturated by the spinor. These are single particle spinor helicity variables associated with the two U's. And to saturate the correct Q factor, which is the E times G, we have to have one pairwise spinor associated with U1 in the monopole and one pairwise spinor associated with U2 in the monopole. So this has exactly the right transformation rule that we postulated. We can try to write the same thing with the same particles. So we could do forward scattering. Can the U1 and the U2 just remain in the instate and not undergo this monopole catalysis? This better be zero, otherwise there's no catalysis. And indeed, the only thing that I can write down that conforms with the pairwise helicity transformation rule is this factor. So this factor is zero by virtue of the selection rule that we wrote down. So you can't stay in the U1 and the U2 that you came. What can you do? You can write down this outstate, which conserves all the standard model quantum numbers and has the right pairwise and regular single particle helicity transformation, and that involves the E dagger and the D3 dagger. And you can go through this and try to write down any other outstate, and it just either won't conserve standard model quantum numbers or won't have the right pairwise transformation rule. So indeed, this is the only allowed outstate in this lowest partial wave. So the cross section to go to that outstate has to saturate the unitarity bound at this lowest partial wave. And of course, when we're talking about the hadronic cross sections, we should address it, and the cross section end up to be roughly the size of the photon square. So to summarize, we solved the problem of constructing manifestly Lorentz covariant S matrix for charges and monopoles. We identified electric and magnetic multiparticle states are not tensor products of single particle states. We also defined an extra quantum number associated with pairs of charges and monopoles. This is pairwise helicity. And we used it to fix all 3-point amplitudes for dyons and charges and monopoles. We also derived the Rubakov-Callan effect from pairwise helicity because there's only one allowed final state at the lowest partial wave, and the one that I kind of knew I won't get to is the proposed solution to what's called the monopole unitarity puzzle, and you're welcome to ask me about it.
Questions for Ofri?
So when you have a scattering, when you have charged particles, scattering of charged particles, already you break the Lorentz group, right? In the sense that you need, say, a string at infinity, a vector to define the Kadesh-Polish state, whatever. But you don't, you have, if you want to take one charge, a pair of charges, you need one at infinity, and you have one vector that doesn't transform covariantly because it's an external object. That was studied by many people, including Frederick. Here, in what sense your S matrix is covariant? Already Fedor Polish breaks covariance. Did one mistake in their paper? It says covariant in 8.
The only violation of covariance would come from the electric Fedor-Polish dressing and its duality transformation, which is G, not an E times G factor. And the E times G photons that we're summing over will not lead to extra Lorentz breaking beyond that.
Now you mentioned S duality. This is just the inversion in the electric magnetic duality. Do you gain anything new or interesting by combining it with the S plus one? I mean, with the,
So these Q's are manifestly invariant under the flow of asymptotically. So you write down an answer which is manifestly duality covariant.
Yeah. High-dimensional version of that story, like goes to 5D, then monopole would be a string. But I would think still there is the analog of Callan-Rubakov effect, that you cut the electron from the string.
Oh, so in the sense of Callan-Rubakov, that's interesting.
But in terms of S matrix, it's confusing because it's not S matrix of point particles now, but
Right. So
one would think there should be some version.
there should be a paper in a week or two. This is this. D branes are mutually non-local. So a P minus 1 and a D minus P minus 3 brane, I think. They have direct quantization associated with the Ramon constant. Everything goes over. So we actually did the vector method of induced representations now for an extended object for a brane. So we had to think, what does it mean to have an orientation of a brane? And what's the little group? I can already tell you the answer. It's just internal rotations cross external rotations, but not rotations that mix in internal and external dimension. And the external rotations are just single particle spin. The internal rotations are something new because particles don't have. But the pairwise phase is the same and works out beautifully because of the dimensions of the brane. So if you take a P minus 1 brane and a D minus P minus 3 brane, and you kind of fix them to some reference state, and you ask what are the additional dimensions. So the additional dimensions are 4D. So now you ask what's the little group stabilizing this configuration. It's again a U1 with associated Dirac quantized pairwise velocity. So this whole story just goes directly to mutually non-local vectors.
Some very nice question. So can this technique also be applied in like electroweak better?
Sorry, I didn't hear which
So
part.
can this technique also be applied in the electroweak better?
Electroweak Farron calculation.
Like the production of the volume number.
I can't think of a direct connection because I don't see a long-range interaction there. And I don't see a deformation of the angular momentum. But maybe let's talk about this offline and see if I'm missing.
Yeah, so maybe even simpler when you have a soliton monopole like in Georgia Glacial, because there you could say, well, I know the theory, I know it can be divided to is a normalizable gauge theory. So, but do you still have this?
Yeah, definitely, because this is an effective field theory. This is irrelevant, irrespective of what's in the core, and then in fact we're producing Callan-Rubakov, which is field theory and topological background.
Is there a 1 minute version of the monopole unitarity puzzle?
Oh, yeah. So great. So that's gonna be half a minute. A lot of the technical details. Good. So the monopole unitary puzzle is, let's say I throw a positron into my gut monopole, and I try to do the same exercise that before when I had the U1 and the U2, there was one possible final state. Now when I do this, it seems like there are 0 possible final states. And that's a problem, and this is why it's a unitarity puzzle. The field theory version of it is even weirder than what I'm showing here, because if you use the same technology that we used for the field theory derivation of Callan-Rubakov, this will tell you that for an incoming 1 fermion, the outgoing state looks like something that has half fermions in it. And you can ask, what are you talking about? And I would say, I don't know what half fermions mean. This is derived in a bosonization language where fermions appear as solitons, and this looks like a soliton of like half the height. But I'm a phenomenologist. I don't know what half a fermion mean. Like I put a detector, I want to detect something. So even though very, very smart people have raised the possibility that there are half fermions coming out of this process. I personally don't know what it means. So we have a different proposal that has some advantages and some disadvantages of what might come out. And what we're doing is we're saying follow our notice. Let's just do this S matrix construction and just try to write down the only valid final state that we can write. So before we thought there's no valid final state because of our selection rule. This part of the amplitude just vanishes. But then we're saying, okay, if every single spinor helicity variable dotted with its pairwise is 0, let's just cross them. Let's just switch them. Contract this one with this one and this one with this one. From the S matrix perspective, that looks like a completely valid final state. What's the physics interpretation? The interpretation is that there's now an entangled final state that comes out. Basically, the spin of the single particle spin of one fermion interacts with the electromagnetic angular momentum that comes from the other fermion. And it's this entanglement that was missed out on the effective field theory Now it has its own problems, so we would be very happy. So I mean, it's self-consistent from the amplitude picture, but to convince people like Montesena, I would have to sit down and write the field theory version of this, which might be pretty hard. But so that's the.
Okay, with that, let's thank Ofri again.